So far here is where we're at with our study of vector field analysis. We know now how to discuss the circulation of a vector field as a vector field in two dimensions, right? And we know it from two different perspectives. We know it from a macroscopic total circulation perspective, in which it is the integral of f dot dr, where that integral is taken around a closed curve. We also, in the case of a two-dimensional vector field so far, we know that we can find a circulation density by taking the scalar cross product of the derivative operator with my two-dimensional vector field. And that Green's theorem relates those two perspectives together, that the total circulation is just the double integral with respect to area in the xy plane of the circulation density function. So that's where we were at the end of last week. In today's class, we walked the same road, but with flux instead of circulation, looking at how a vector field flows across a curve instead of along a parametrized curve. We have a measurement of total flux, which we can compute as the integral of f dot dr, but that r is a unit vector so that we get the right units on our flux and independence of parameterization. But the better way to think about how to find a flux across a closed path in two dimensions would be to trade out flux for flux density, my microscopic measurement. And that flux density is called the divergence. It's the dot product of the derivative operator with my two-dimensional vector field. And then it's the divergence theorem that relates these two perspectives one to another, that the total flux is equal to the integral with respect to area in the xy plane of the flux density, in other words, the integral of the divergence in the xy plane. So that's where we're at so far, and the last step that we're taking in vector field analysis is just to take these ideas and bump them up one more dimension, from 2 space into 3 space, so that we can talk about the circulation of vector fields along closed paths inside of 3 dimensions, and if it might be easier to trade out that closed loop circulation in 3 dimensions for some kind of a double integral of a circulation density. So how can we get away with doing that in 3 dimensions? And similarly, if I want to know about the flux of a vector field through a surface, is there a way for me to trade that out for an integral of the circulation of the flux density, rather, on an appropriate region inside of 3 space? And so that latter result is still called the divergence theorem, even when we see it in 3 dimensions. But because of the ambiguity in going from a closed path in 3 space into some surface whose boundary is that closed path, there's a lot of different ways to do that. And so that theorem gets a new name. It gets called Stokes Theorem. And it's the last of our integral theorems that connect these various perspectives together. So that's what we'll do in tomorrow's short class, leading into Thursday's full class. And that'll be how we wrap up our new material for the semester.